So, welcome to this tutorial on web stream processing. We will cover basically an introduction on the concepts of web stream processing, and then we will dive into two technologies. One is called RSP4J and one is called OntopStream. The presenters are Pieter Bonte, who is a postdoctoral research at the University of Ghent, the IMEC lab, and is an expert in graph stream processing, data inference and semantic technologies. Is the maintainer of RSP4J, and it is the author of several interesting works on web stream processing, specifically CEST and streaming massive. He has 8 years of experience in innovation and research projects. Then there is Matteo Belcao, a student of mine, is a data engineer, is working at Quanta Consulting, is an expert in ontology-based data access and in stream processing technologies. He's the author of Chimera Suite. You may want to check it out on GitHub, but you will have opportunity to see it during the tutorial. He has 2 years of experience in research and innovation projects. And I am Emanuele Della Valle. I am an associate professor at the Department of Computer Science in Politecnico di Milano. I'm an expert in semantic technology and stream computing. You may have heard my name connected to stream reasoning, which I branded something like 12 years ago. I have more than 20 years of experience in research and innovation projects, and I also a startupper. Okay, so very important preliminary step. This is not just a screencast. There is the opportunity to put your hands on contents that we will demonstrate with you. They require Docker and Docker Compose. So if you don't have them installed on your Mac, on your machine, sorry, please do install Docker and Docker Compose. All the content that we are proposing, so the slides and the tutorials, the hands-on, they are all present in a repository. This is the link, but you can also find the link on the web page of the tutorial. Please clone it and start from there. Otherwise, if you don't have the opportunity to use Git, you can also, of course, download the zip from the website. I see that Pieter sent the link to the repo to the chat, and so feel free to open that one. Okay. So, getting into the introduction. I think you all agree that nowadays we contain many of the characteristics that somehow shape the concept of big data. Hadoop, MapReduce, Hive, Spark, the data lake concept, all of them somehow are ways, technical and methodological, to tame the volume dimension. We can also tame the so-called velocity dimension thanks to a number of engines that did a very important paradigmatic change from persistent data and transient query, which is what normally you have in any system that is oriented to historical data, to persistent queries and transient data. And so you register somehow the query in your system, and that is present since the beginning, and then the data will pass through your system. Unfortunately, you cannot tame volume and velocity simultaneously, or at least there is no way to tame the full space of velocity and volume at the same time. Here, what we are trying to say is that nowadays, it will be possible to process kilobytes of data in nanoseconds, and of course, it will be possible to process exabytes of data in days, but exabytes of data in milliseconds, that's no way to go. So it's like there is a sort of Chinese wall that does not allow you to go in part of this space. It doesn't really matter if, I mean, the line is exactly where the state of the art is. What matters is that it is, of course, not technically possible at a certain point in time to address any sides at any speed. What really somehow characterizes the tutorial that you are going to follow is the ability to tame variety. And specifically, we claim that among all the different technologies that you can use in order to tame variety, especially I'm not going to talk about artificial intelligence where you see natural language processing, image recognition, and so forth. We will talk about semantic web technologies. Specifically, we are somehow assuming that you have a notion of what the RDF data model is, what Sparkle query language is, how you can use an ontological language like OWL in order to model the domain in which you are somehow capturing data and knowledge. And then you will see there is a language, mostly Matteo will talk about it, it's called R2ML, that allows to access relational data using an ontological approach. And there is a methodology, ontology-based data access. We are going to refresh what these concepts are for your convenience if you're not, too familiar with that, and then we are going to build on top of that. But before, let me stress that if there is here this trade-off between the maximum speed and the maximum size at which you can process the data, whenever you bring variety and veracity into the shape, what happens is that the trade-off is going to get even lower. So in a sense, it is extremely challenging to address simultaneously the 4 V's. We are not going to address veracity in this tutorial, but indeed we are going to address volume, velocity, and variety at the same time. We do that because in our industrial experiences, we run into a number of use cases where we saw that all the V's are required. Just to give you an example that I think fits very nicely to this web stream processing tutorial, in an event that happened back in 2015 in Milano, we deployed these technologies for a very long-lasting 6 months. And of course, with millions of visitors, event that is called the Universal Exposition of Milano 2015. The kind of visualization that you see up there, the squares are pavilions, the dots are social media interactions, then the boxes, as you can see, get darker or lighter depending on the amount of social media people present and so forth. So I think that you can see that this is volume, right? Because indeed you have hundreds of thousands of people present, and is also velocity because they keep leaving digital footprints over social media, phone calls, Wi-Fi, and Bluetooth. And in the peaks, we were experiencing even up to tens of thousands of digital footprints per second. And what we were doing during this real world deployment that we did was suggesting where to go, to which pavilion go in order to somehow address some need that the user have, depending on the interest and depending on the presence of people to the pavilions. I hope this was at least motivating, if not convincing. So in a requirement analysis that we did back in probably the end of the 2000s and the beginning of the 2010s, what we did was trying to get many problems like this one. Okay, we were also surveying probably 5, 6 other domains, and coming up with a list of abilities that systems that want to address those use cases must have. First of all, handling a massive data set, which is indeed a volume problem. Then processing data streams, so flows of data that keep streaming on the fly, which is a velocity problem. Coping with heterogeneous data set, which is the variety problem. And then comes the more complex things that somehow prevents to do the solution, to find solution easily. First of all, you cannot assume that the data are complete. There will be always incomplete. And part of this incompleteness can be somehow fixed thanks to models of the reality that you have. And in other cases, simply missing information. So it's a veracity problem. Then there is the noisy dimension. So indeed, even in social media where you try to get the intentions of your user through the text, the images that they post, it might be hard to be sure that you understand what they want. There might be irony into what they do that somehow will trick your artificial intelligence that tries to guess the intention. Most importantly for us, there is the need for reactive answers, which means that you want the answer to arrive before more information will make it useless for the system to give you an answer. So a new answer should arrive. And then there are the last two, which are about the nature of the answers, because we are not going, as in early velocity-oriented system, only to do aggregates. What we want here is to provide fine-grained information access. So in the case of a social media example, analytics example that we did in the previous slide, the idea is to recommend for the specific user exactly the set of possible events in the set of possible pavilions nearby where we want him to go. And that will be, if we have hundreds of thousands of concurrent users, a prediction for each of them. Last but not least, because we want to interpret the real world thanks to domain knowledge, we need to be able to integrate complex domain models that capture such a knowledge. Okay, so with those requirements in mind, what we did was trying to understand whether the state of the art was up to the task. What we discovered was that indeed data streams management system were good enough, because they were able still, okay, when we brought them into the picture back in the end of the 2000s, to process data one data point at a time in a way that they really, solve the velocity problem. And indeed, as I was mentioning before, they do it through a paradigmatic change from this persistent data and transient query to transient data and persistent query. This picture down to the bottom right of the screen is illustrating the main idea. So you have this dynamic system, which is a piece of reality that generates your data. You are observing those data through sensors or through connections to them. If this dynamic system is the social media world, those streams are queries that you register into the social media systems. But as you will see during the remainder of a tutorial, there might be also other ways to collect the data. The stream goes into a so-called window that is the logical abstraction that allows the registered query that you have down into the bottom part of the image to somehow look into the flow of data, capture a finite part, and generate an answer. So as you can see, while the data stream through the logical window, we generate a stream of answer as a result of the query. This is really something important that was somehow understood back in the late 90s. And there are a number of systems that use this idea. The two well-known ones are the so-called data stream management system, DSMS, and complex event processor, CEP. Just to bring you into this world as fast as we can, image that this set of boxes down to the bottom of this image are somehow data points that arrive to your system, and the more they are to the right, the more old they are, and the more they are to the left, the more newer they are. So we have a window that is opened from now back 1 minute in time. And what we can do is basically assuming that the data will pass through the window, okay, and while the query somehow is registered, we will get answer as a flow. So one possible question will be, which are the top 4 most frequent boxes in the last minute? That of course requires to open this 1 minute wide window. And then you go and you look into the colors, and you may have an answer that it is, for instance, there are 13 green boxes, 12 red boxes, 8 blue boxes, and 8 light blue boxes. It's important to understand that while the data pass through the window, the answer will change. As we said before, it will be a stream of answers. Okay, now there are multiple types of windows. So I told you that they are logical abstraction, and indeed you can specify them based on time. So I want the last minute, based on numbers of events. You want the last 10 events, and then you can tell how they move. So they can tumble, meaning that they cut the stream in slices that do not overlap, or they can slide, meaning that they cut the stream in overlapping slices. A newer type of window that I really think is useful in several settings is the so-called session window, where you specify the maximum distance between 2 consecutive events that will put them into the same window. And so you say, I want all the events that are not separated more than 1 minute. And so as far as the events do not get more distance than 1 minute, the window keeps opening. And then if one event comes after, I don't know, 2 minutes, then there will be a closed window and a new window will open with a new event that arrives. I hope that this was clear and not too fast. One important thing to understand that we will demonstrate during the tutorial is that joining streams is extremely hard on time. Of course, joining streams on time is extremely hard because you cannot assume that the data are synchronized, so that they come exactly at the same time and exactly with the same frequency. Here we have 2 streams, S1 and S2. They come with different frequency. S2 is definitely more frequent than S1, and as you can see, the pins, okay, that represents event over time, they are not aligned. So if you do a join on time, the point on S1 will never join with the point on S2. And so if you do an inner join, the result will be an empty stream. So what? Well, so you need windows again. This purple square, that is a window that is capturing 1 event in S1 and 2 events in S2. And those are the events that, of course, when there will be a key predicate, you may want to join. And then the window will tumble in this specific case, and you will cut the 2 streams in 2 slices that contains the event that you want to join, and that will somehow keep happening, right? So in a sense, what we try to tell you is that windows not only are important as an abstraction that make it possible to cope with the unbounded nature of data streams, but also that windows become extremely necessary when you need to do some typical tasks of data stream processing, typical task of data processing, live joins, that in the case of data stream processing are non-trivial because of the nature of the operation that you want to do. Okay, so if we compare the requirements that we elicited in the analysis of different scenarios that requires to tame volume, veracity, velocity, and variety, and we compare them to stream processing, what we have is the following: that indeed this system were made to scale, so they tame massive data sets, they were built for velocity, so they work with data streams, and they normally are able to cope with noisy data to provide reactive answers that are fine-grained. Then they do not come with an explicit way to solve the problem of heterogeneity, meaning that exactly as in databases, either you design a data stream management system or a complex event processor application to cope with a given type of data, or the system would basically require you to do integration. And the fact that you don't have a technology to do integration is what limits you. They also don't work with incomplete data because they assume complete data as in databases. So they assume the so-called closed word assumption. And they don't have the complex domain models. So everything is somehow hardwired into the queries that you write as in standard databases. Now, we said that the other part of a solution are semantic web technologies. So let me try to show you in the example that we did before why we may want to benefit from them, and then we will blend the two. So when we talk about semantic web technology, of course, even if we have some stream of data, we cannot assume to have windows because the concept of window is not present in the semantic web, or at least it was not present in the semantic web 10 years ago. But you have ontologies, right? And the power of ontology is the following. You may ask questions that are related to the terms of the ontology. Here, for instance, we have an ontology of colors that presents a number of colors and categorize them into warm and cool colors. Okay, and the question will be, are there any cool colored boxes? And then you look into the data and you provide an answer. So yes, there are light blue and dark blue answers into our data. So the interesting thing is that you ask for something that is not explicitly represented in the data. The system reasons on the conceptual model, in this case, the conceptual model of the colors, and deduces that if you're looking for cool colored boxes, you're also looking for blue, blue-green, blue-violet, violet, red-violet boxes, right? And therefore it matches the real data that come into the data set. To recall this to you, the data model is called RDF, Resource Description Framework, and somehow comes in the form of triples where you have a subject, a predicate, and an object. So a very basic social media post will be the author of a post, Alice, that's the subject, the action, posts, and then the content of the micro post of a post will be the object. In this case, Alice is posting that she is with Bob. A collection of these triples make a labelled direct graph that in RDF terminology is called an RDF graph. And we may have a lot of this data collected in order to, create a very large sets of data that you want to share over the web. Now, In this setting, ontologies are extremely important because they allow you to give names, interoperable names to the entities that you want to represent. For instance, in the specific case of social media, you may want to say that posts is a property and that post is a sub-property of communicates. And also you may want to say that those who post are social media users and so forth, right? In that sense, you allow a machine to understand a bit the data structure, and you enable the kind of reasoning that I was demonstrating before using the example of the colors. You ask for something, for instance, you ask for, is there anybody that is communicating? And the system will reason about this. The idea is that therefore you need a query language. It's called Sparkle, the query language. And the Sparkle runs both in, let's say, database-like mode, so you ask to match triples, but also runs under reasoning condition, but those are called entailment regimes. To give you an example, if I ask what does Alice post, I will write something like Alice post and then question mark X, where I'm meaning that I know the subject Alice, I know the predicate posts, and I'm looking for the object X. And this can be answered directly on the data. Whereas if I say, what does Alice communicate? Then I'm going to use the communicates predicate that is not present in the data, but I can get to posts going through the ontology. I'm gonna say that in the next slide, how we can be done. Another example is there a social media user, meaning that you ask for X of type social media user, and again, you may get to answer that there is Alice because somebody who communicates is not a social media user, but somebody who posts is a social media user. So because we know that Alice posts, I'm with Bob, Alice is a social media user. A collection of these triple patterns is called a graph pattern, and is the basic component of this Sparkle query language. As I said, we will show some reasoning, and specifically the part that Matteo will demonstrate is called ontology-based data access, and it works in the following way. The idea is that you put queries against the ontology, and then you provide mappings between the ontological terms and the data sources. And what the reasoning does is to take the SQL query, the Sparkle query, and rewrite it down into a SQL or more, one or more SQL queries. This is also called the virtual knowledge graph approach, because from the top, it looks like you have a huge knowledge graph that is made of billions of triples that you can query through Sparkle and ontological terms. But in practice, this gets reduced down into using stable and highly optimized SQL technology. Just to give you the impression of how this works, image that somebody asks, what does Alice communicate? So it writes, Alice communicates Y. And then you have this knowledge captured in the ontology that post is a subproperty of communicates. Therefore, you know that somebody that is asking, does Alice post something, okay, will somehow find an answer that is also an answer of Alice communicates something. And therefore, if you know that you can create triples of a type, a user posts a given text through a query that gets down to a table posts that contains two columns, user and text, then what you can do is rewriting the triple pattern Alice post Y into a SQL query like select user and text from post where Alice is the user. So the basic idea is that you provide mapping And then you can somehow put more constraints of those mapping through the Sparkle query, and the reasoner will reason on the knowledge captured in the ontology and rewrite it down into the system. I know that this was fast, but I hope that you have at least the impression of how it works. Now, if you compare semantic technologies to the requirements, more or less you have the opposite as before, because semantic technology are made to cope with heterogeneous, incomplete, complex domain models, and on the same side, somehow they provide fine-grained information access, they scale, with the ontology-based access indeed is a way to scale to very, very large data set, but then they do not have a way to cope with data streams, and of course, noisy and reactive answer are also not in scope. Or at least this was the situation back in 2008 when we started this field and we were thinking about how can we blend the two. Indeed, we frame the web stream processing research question as the following. Is it possible to process in real time multiple heterogeneous, gigantic, and of course, inevitably noisy and incomplete web streams? Now, as I said, we are going to help you understanding this technology, put your hands. So if you have not done this before, when I started the section, please download Docker and Docker Compose, check out our repository with the content. And because it takes a bit to set up the environment, and we are going to put the hands on in a few minutes, please also do the following, okay? So once you have a repo on your machine, open a terminal, navigate to the right folder, which is the exercises, specifically part 1, and bring up the entire stack saying Docker Compose up. Okay, so what's the perspective of this web stream processing from a user point of view? Well, the idea is that now you have ontology, but you also have the windows. So what you can do is registering queries that somehow benefit both from the streaming ability and the ontological ability of the system. For instance, if you say, which are the top 2 most frequent cool colors in the last minute, what you have is again a query that cannot be directly asked to the data because there is no box that is tagged as cool, but there is an ontology that allows you to know that it means that you are looking for blue boxes, green boxes, violet boxes, and so forth, right? So you can reason on the question and register a more larger but syntactically matching query, and therefore you will get the answer that you expect. To do that, you need to extend the data model, and what we did was introducing the notion of RDF streams. And here there is an example where you have the triple of before, Alice posts, I'm with Bob. And the most important point is that it gets time-stamped. So we are adding a 4th element after the triple, which is the timestamp of the triple. And an unbounded sequence of a time-stamped RDF statement that is what we call an RDF stream. A continuous query will be what you need in order to process a stream, right? So we also created a language that is called RSP query language, and what this query language allows you to do is to register queries against RDF streams. Here specifically, we are registering a query that counts the number of social media posts that are done by different users over a window of 1 minute. And so the semantics, the intended semantics will be something like who have been the most active user in the last minute, because you are somehow counting per each user the number of posts, and then you can order them and get those that post the most. The difference, if you know Sparkle, is in this closes register stream, where you are registering the query, and from window on stream, and then the syntax range 1 minute, step 1 minute, that allows to specify the window over the RDF stream. So the semantics of this RSPQL builds directly on the one of Sparkle, but it introduces the notion of from stream, and it actually redefine the semantics of all the query form, constraint, describe, select, stream, and ask, so that you can do the usual Sparkle queries and registered queries that create streams. Oh, what's the dream? Well, the dream is that the more we will progress with the technology, the more complex the ontologies could become, and therefore the more expressive the system will be. In this specific example, just to evoke the idea, we show to the right an ontology of the connection of the words to the colors. So every word that you read in the box is a word that somehow is mapped to one of the colors, and therefore if you say which are the most frequent sentiments, assuming that ontology connects words to colors in the last minute, what you have is understanding, right? Because it is somehow the combination of the colors that is appearing into the last minute window. Okay, I think I leave the ground now to Matteo to do a demo. We call it color wave because we are going to demonstrate over, a very simple synthetic streams of colored boxes, the queries that we were showing before. So Matteo will first create a query that counts the number of warm and cold colors, demonstrating this basic idea. And then it will also show you that you can indeed create new RDF streams by combining existing ones. But I leave Matteo the ground, and please remember that you should have downloaded the system. You should have gone, if you want to do this yourself, with a terminal into the exercises part 1 of the repo that you downloaded, and Docker Compose app is the command you need to get everything started. Matteo, will you share the screen?
Yes, of course.
Okay.
I will share my screen.
Yeah.
Okay.
I'm trying to. Okay, you made it. Good.
Do you see my screen?
Yes, we see your screen.
Okay, good. So I will assume that you have cloned our repository. So you have opened a terminal and you have gone to the right folder. So using cd exercises part 1. The next thing we need to do for starting our demo is to bring up the stack using Docker Compose. So if you run this command, if it's the first time, it will make a little bit of time because it will download all the stack from Docker Hub. Otherwise, you should see something like this at the end of the process. So let's see. You should see creating all the environment. You should see here until you should see a lot of words appearing, which are the several components of the stack. Given that you see all these writings, you can open a new browser tab and go to localhost 8888. So you go to, maybe let me open a new tab. Okay. So you go to this address here that I will put also in the chat. And here you should be able to see two notebooks comparing warm and cold colors and the cooking grain streams from yellows and blues. So starting from that, let's see the first notebook, which is the introduction to RSPQL, which is the RDF stream processing query language. And in particular, in this notebook, let me open it. We will see how to create a window with a given time span. And in this window, we will ask for those to count all the warm colors and the cold colors. How we can distinguish between if a color is a warm or cold, we will base our, let's say, our reasoning task on an ontology, which is already available. So starting from the execution of the first cell, where you can start here, what we have to do is to inspect the sources. So here you can see that we have a little description where basically it says that there is a web server which exposes our stream of colors. So by clicking this link, you should see something like this, which is the description of our stream, with all the information in JSON LD. While on the other, and in particular in this link, we can see that this stream is accessible using this WebSocket URL, WS color stream 5555, which is the address of our stream of colors. In particular, we can take maybe just to show you that what we can do, we can try to connect through WebSocket to this color stream and see that this is a service that I can just show you for the demo, for the purpose of the demo. You don't need to do that. We can see that by connecting to this on localhost 5555, we have a stream of color which are constantly generated by our data generator. You can see here a lot of RDF data generated in real time with our colors. So given this data, what we'll do now is to query that and decide if to count every RDF information we get from this stream, if it's warm or cold. So let me close this and let me go back to the notebook. And let's see how we can create our query. So first of all, we need to import our engine. So we need to import the RSP engine. And in particular, we will use Jasper, which is an RDF stream processing engine. There exist several RDF stream processing engines. Jasper is one among the others available. And once we have imported the engine, we can define the query to decide if let's say if a color is warm or cold, and the counting process. So first of all, we need to assign to our query an ID. In this case, we call this query, for example, reasoning. We'll assign attributes ontology, which is the color ontology. So if you copy and paste this on your browser, you should download an OWL file. Here is all the process is made automatically, but in practice, this is a link to the ontology, which decides if a color is in the cool spectrum or in the warm spectrum. Okay, so here is the ontology. And finally, we need to define our query. So we define an RSPQL query, which is very similar to the Sparkle syntax, except for the fact that we have a more richer syntax that will allow us to express window conditions. So given our task, we can make a selection counting the warm colors as in the variable warm count, and the cold colors as cold count. Define our window, which is named color window, and is based on the stream exposed by this endpoint here, HTTP color stream 8080 colors, which goes back to the WebSocket stream of colors we have seen before. And then we can define the time span of the window. So we define the first parameter, which is the white, and then if the second time parameter, if the windows are overlapping. So here, in this case, we are defining several windows with a white of 15 seconds, which are generated in an overlapping way every 5 seconds each. So every 5 seconds, a new window will be created and will last for the next 15 seconds. And finally, in the where close, we are just selecting from our color window stream the warm colors, where warm is a variable containing the entities which are of type warm, so colors warm, based on the ontology. And on the other side, we also select in the cold variable the entities which are of type cold, based again on the color ontology we have defined in the tbots. So given that, we can execute this cell and then start to register our query. So we compose our query with jasper.create. We pass all the parameters. We set the output to JSON. And we can see we can see that we have our reasoning query, which is ready. The next thing we need to do is to define the streaming endpoint. So how to receive our response from the stream. So we need just to see that, you can see that we don't have an endpoint to receive the data. So we need to create a receiving endpoint to receive all the responses of the query. So in practice, we use Jasper again, jasper.expose. We pass to it the query ID, which is registered in Jasper. We set the HTTP protocol because we are working with a WebSocket. And given that, we are able to receive our responses in our notebook. So now, if we use the primitive response.endpoints, you should see Jasper the get over the Jasper endpoint. So the stream now has an endpoint, you can see here. And this endpoint is providing us the responses. So if we execute the next cell, we can see that we have some data coming. So you can see we get some data. So this is JSON LD data. You can see that is quite complex, but you can see that in every response, for example, here, this is a response to a single window. You can see that we have two counting, which are our goal. We have a warm count, which has a value of 25, and we have a cold count, which has a value of 5 elements, and so on. So you can see going down, we have a lot of other countings. And if you want to print in a more readable way, we can also use this other code to print the results of all the windows we have received the data so far. So if we go up and if we re-execute the cell, we can see that if we re-execute also this one, we get the data from other windows. Okay. So in practice, these are our windows generated by the data generator. Finally, we can just make a plot and have a look of the percentage of cold and warm colors. Finally, we can delete our our stream using Jasper.delete. So in this case, by passing the query ID, we are saying to Jasper to delete our RSP4J query we have defined before. Okay, and this was the first notebook. The next one is cooking green streams from yellows and blues, which is another notebook where we accomplish another task. So here in this second notebook, what we will do is to create again a window, a set of windows with a given time frame, for example, 15 seconds. And in this window, we are asking to create a new element, which is the green color, if are present a blue color and a yellow color. So every time our query in a given window will find a set of blue plus yellow color, it will create a new green box, a new green color. And this will repeat for all the windows. So here we have again this code, which is the inspection of the sources, which is the sources are again the color stream. So it's the same stream as before. The interesting part is the query. So here is exactly the same code. Here is the different part. So you can see that here in this query, which is, we will call it green, we have this query is based again on the color ontology, so the same ontology of before. But as you can see here, we have another syntax, which is a little bit more complex. So just starting from the bottom and then going to the top, we can see that this part here of the query is quite similar to the one before. So we have the definition of a window, which is extracting some, which is, let's say, selecting a union of yellow and blue colors, which are matching the definition of the given ontology. So here the query is quite similar as the one before. Then we have a bind, which creates a unique identifier in the green variable. And then we have the interesting part, because every time this part here of the query finds a yellow and a blue and generates the unique identifier with the green in the green variable, this green variable will be used by the construct primitive of RSP4J to create a new graph entity. So here we will create a new RDF streaming data, and we are saying that this new green variable is of type colors green according to our ontology. And we are also saying that this green entity is composed by a yellow entity, which is in this yellow variable we have extracted from the where clause, and the blue entity, which is given by this other part here of the where clause. So you can see that this query is able to take the data from the stream and create new data given from the data already available. So let's go a little bit faster. So here we have again the stream which has no endpoint. So we have again to create our endpoint with again Jasper. And the interesting part is here. So we don't have green colors in our stream, but if we now get the data from our response, it will take a little bit because it has a little bit of reasoning and the construction. We can see that we have a response with the several green colors. You can see from every color has a unique identifier. You can see here every green colors has a unique identifier. So for example, this here is an RDF entity representing the green colors. You can see it has an ID. It is of type colors green according to the color ontology. and is made from these colors here. Okay, so you can see that we have managed to create new data from the existing stream and put them in a streaming fashion. Finally, we can delete also this query by just using jasper.delete. Okay, given that, to just the last part, just to not overlap, to close this the demo environment, you can use a Ctrl+C to stop all the notebooks, all the platform. So you press Ctrl+C on the terminal, and you should see something like that, stopping all the components. And let's wait that it will stop. Okay, and finally, to use also the docker compose down command to remove all the components from Docker. Okay, I think we have managed this part here. I can leave.
Thank you, Matteo.
The control to Pieter.
Yeah,
Yes.
indeed.
Thank you,
Pieter.
Okay,
Matteo. Let me find my screen. There we go.
okay, we see your screen.
Okay.
Yeah.
The controls for Zoom are in the way. Yes, perfect. Okay, so hello everyone. My name is Pieter Bonte, and welcome to the second part of our tutorial, web stream processing with RSP4J and an OntopStream. And this part will focus more on the internals of RDF stream processing, and we'll do some exercises with RSP4J library. So on the agenda, we'll be looking at some of the background of stream processing. We'll be looking at operator families using the CQL model, and at introduction of the execution semantics of the secret model. We'll look a bit deeper into RSPQL, and then investigate some of the internals with the RSP4J library. So there will also be demos and exercises. So if you want to follow along, because we will do them with RSP4J, and RSP4J is a Java library. So if you want to follow along doing some of the coding exercises, make sure that you have Java and Maven installed. If you don't have any experience with Java, or you don't have Java on your machine, do not worry, because you can still do the exercises manually on paper or something like that. But if you do want to follow, please make sure that you clone the...
Sorry, Pieter,
yes?
we will see only the intro page.
Oh, really? Okay. Do you see it now?
I think that the mouse, I mean, the screen gets...
It's frozen?
Yeah, because
Okay.
I see that the pointer is stuck on play. I mean, that's what I see. I don't know what you see, Matteo.
Yes.
Okay, now
it's okay.
Yeah.
Okay.
Now we see
Not sure
the
what
agenda.
happened there. So anyway, so for the agenda, yeah, I was explaining. So if you want to follow along with the exercises, please make sure that you have the repo cloned and go to the right folder. There's also QR code if you're easier to get the material. So anyway, every time that you need to go through some new background, it often feels like you need to climb a very steep mountain. And today we'll climb the mountain of stream processing, but do not worry, I will be your guide and aid you all to the top with ease. And the first stop along our climb will be the introduction of the SQLs model, and we're talking about a paper titled The SQL Continuous Query Language, Semantic Foundations and Query Execution. It's a paper by Arazu, Babu, and Widow. And basically, when you want to define the semantics, or like the underlying fundamentals of a stream processing or a continuous language, engine, you can either do two things. Either you can start from scratch and try to incorporate all the complexity of the streams internally, or you can try to somehow bypass the stream complexity and try to do some kind of transformations to things that you already know. For example, more static things such as databases and relational algebra. And the last thing is specifically what the CQL model is proposing. But before we go into details, let's first introduce some abstractions. And the first thing I want to introduce is the concept of a stream. And a stream S is a possible infinite multisets of elements S and T, where small s is a tuple belonging to a certain schema, and T is a timestamp. So we'll again be talking about the stream of colored boxes, where each box is a tuple belonging to a certain schema, describing, for example, the spectrum of the light and the frequency, and also the specific color. For example, the color green has a spectrum between 520 and 565. Another abstraction is the idea of a time-varying relation. And a time-varying relation basically is a mapping from each time instant in T to a finite but unbounded bag of tuples belonging to a certain schema. So the idea is that we have a mapping from time to relations. Now, the reason for this will become clear in the next slide. So, as I said before, the CQL model basically tries to do some transformations going from streams to relations, because we can process relations with things that we already know, and that wants to go back to streams. And therefore, it uses three kinds of operators. The first operator to go from stream to relation is called the stream to relation operator. For example, a time-based window. Once we're in the realm of relations, we can use relation to relation operators. For example, relational algebra is something that's been well studied, and it makes sense to try to reuse these things. If we want to go back from relations to streams, we can use the relation to stream operator. And this allows us to go back from streams to relations and relation to streams and reuse the things that we already know, and still allowing to do processing and understand fundamentals of processing continuous queries over streams. Because that's maybe a bit abstract, let's do a visual explanation. So on the bottom, we still have our stream of color boxes, and we'll go to the different operators. So the first one is the stream to relation operator, which is basically a time-based window. And the time-based window is actually more or less like chopping the unbounded stream in possible chunks. So it's taking part of the stream so that we can process it, for example, with the R2R operator, which is counting the number of boxes. If we would do this on the whole stream, it would be mostly impossible, because we would have to wait. We wouldn't know how long we would have to wait till the stream has been reduced completely, because the stream is possibly infinite, it's unbounded. So we can't wait till all the boxes have been produced in order to count them. So therefore, we're using windows to extract processable chunks. So the R2R operator can do some counting on the content of the window. In this case, we have two blue boxes and one red one. And then the R2S operator allows us to stream out results again, for example, by assigning a timestamp. Now, there are different ways to stream out the results. The first one would be the R stream. And the R stream basically allows us to just stream out the results in the result set. So in this case, we would stream out one green box and one red one. Another option is the I stream, and the I stream will stream out all the new solutions in the solution set. So previously we had two blue boxes and one red one, and now we have one red one and one green one. So the green one is new. So the I stream will stream out everything that's new and add a timestamp. And similarly, we have a concept of a D stream, and a D stream will stream out everything that has been deleted compared to the previous solution set. So we had two blue boxes and one red one, and now we have one red one and a green one. So the blue boxes have been deleted, and the blue boxes will be the ones that streamed out by this D stream R2S operator. So this brings us to the idea of continuous semantics. And continuous semantics, if you would have a dictionary to define all the concepts in stream processing, would be the result of a query is the set of results that would be returned if the query were executed at every instant in time. Of course, executing something at every instant in time might seem impossible, but we'll get to that in our next stop. So we have been climbing our mountain of stream processing, and I think we're almost in the middle, and we can already see the top ahead. So let's keep climbing. And our next stop is the secret model. We'll be looking at a paper called Modeling the Execution Semantics of Stream Processing Engines with Secrets, a paper of Dinar, Tabul, and Miller. So basically, the execution semantics describe how a data system or a stream processing engines behave over time. It describes what results are being computed, where in event time are they being computed, when in processing time are they being materialized, and how do earlier results relate to later refinements. Now, to keep things simple, we will not be investigating any distributed approaches such as the data flow model does. So we'll mainly focus at what results are being computed and when in processing time are they being materialized. And this allows us to focus on the secret model. And basically the secret model is more or less like an analogy for the metronome that you have and that are basically telling musicians when they should operate their instrument. Basically, the secret model is instructing when a processing engine should be activated. And we see two different important aspects here is a tick and report. And the tick tells the system when it should start processing. And there are three options for a system to start ticking. The first one is time driven. So when an event arrived with a new timestamp, the system can be activated. The other option is tuple driven. So when a new tuple arrives, a new event arrives, even though it might have the same timestamp, the system can be activated. And then another option is batch driven, which is basically a combination of the two. So each time an event arrives or a color box arrives, in our case, it's added to the window, and the window has a certain content. And there are a number of reporting policies that decide when the content of the window is reported to the downstream operators, for example, the R2R and the R2S operator. And there are different options to do this reporting. The first one could be on content change, meaning every time something new arrives in the window, we can report it to the downstream operators. Another option would be window close. So if you have a time-based window, it typically has an opening and closing time. For example, if you have a window of 10 minutes, after 10 minutes, the window will close, and then the content, which is all the elements inside the window, can be reported to the downstream operators. Another reporting policy is non-empty contents, meaning that we only report when the window, when there is at least one element inside of the window. And then we have periodic reporting, for example, at predefined time instances. Now, the neat thing about this is that you can combine these different reporting policies. For example, the C-Sparkle engine is operating under window close and non-empty content reporting policy. All right, so we've talked about continuous semantics. We've talked about execution semantics. So we've climbed this mountain of stream processing. Unfortunately, this talk is not about stream processing directly, but about RDF stream processing. So there is still a steep climb ahead of us, but it's clear that we're almost there, going through the background. So for stream processing, we had this idea of SQL with the family of operators going from streams to relations with the different operators. Of course, if you look at RDF stream processing, of course, we have RDF streams and we have RDF graphs as a static counterpart. But the RSP4J model, which is the theoretical foundation beneath RDF stream processing, is using the same kind of operators from the SQL model. So we also have the stream to relation operator to go from RDF streams to RDF graphs. We have relation to relation operators to operate on top of these RDF graphs, and we're using Sparkle algebra instead of relational algebra. And then we can stream out the results again using the relation to stream operator. So if looking at the abstractions, before we had this time-varying relation. So in this case, we have time-varying graphs. So we have these functions going from time instances to graphs, and a graph at a specific time is then called an instantaneous graph. So a data set in RSPQL can be a combination of multiple time-varying graphs, but also, for example, named graphs, default graphs, more static graphs, which you have in a typical Sparkle dataset. So how does it look like? Before we had all these boxes, all these colored boxes, because now we have a stream of RDF, so RDF stream, we have a stream of RDF graphs describing different colors. But the operators are the same. We have the stream to relation operator, which allows us to window the content of the stream. And then we have the relation to relation operator, which in this case is Sparkle algebra, for example. In this case, we are using a triple pattern just to query the different colors. And then using the R2S operator, we can stream out the result of the triple pattern, which in this case is a table of bindings. All right, so in the introduction, we already talked about more or less the structure of a Sparkle query. So basically, it consists of 3 clauses. So the data clause allows us to define where the data should come from that needs to populate the data set. So we can have, for example, data from the web, data from file, and so on and so forth. The where clause defines the patterns basically that you want to define on top of this data set. And then the combination of these two, like the patterns, the triple pattern, the basic graph pattern, and the data set, they generate some internal bindings, which you see on the right-hand side. And the query form allows us to define what the result should look like. For example, if we have a select, basically you have a table as a result, and if you have a describe or construct, the result is a graph. Now, RSPQL, as already discussed, is extending the Sparkle syntax. And basically, we also have a way to populate the data sets, which in this case is called the streaming data set, with graphs, but more specifically with time-varying graphs, which is like the windowing counterpart of the stream. So if we look again at an RSPQL query, it's very similar as the one we saw in introduction, to analyze who is where, or in Facebook check-in stream. But most important parts on the second line, we see that we have register R stream on a specific stream. So this is the definition of the relation to stream operator. On the second line, we have the query form, which is a standard select, which you have in standard Sparkle. And then on the next line, we have the from named window clause, which allows us to define the stream to relation operator. So here we're defining window W1 on a specific stream. So the stream name is defined there, it's a Facebook stream. And then we have the definition of the window parameters. So in this case, it has a width of 1 second and a slide of 1 second. So it's a tumbling window of 1 second. In the where clause, we can target specifically this window. So we can define a basic graph pattern in this case, looking for all the persons who are another person who are in a certain room. So this basic graph pattern will be executed on the contents that is the result of the windowing operator. So like this, RSPQL allows us to define all the 3 operators declaratively in this extension of the Sparkle query language. So what about the results? So we know that when we have a select query form, the results are bindings. So the results of RSPQL in this case would be time annotated collection of bindings. If we have a construct clause, the result would be time annotated triples or time annotated graphs. So both are possible. Different engines are adhering to different options here. But of course, time annotated graphs are more generic than time annotated triples. Okay, so now that we learn a bit more about RSPQL, let's introduce 2 existing engines. The first one is C-Sparkle, and C-Sparkle is using what we call a so-called black box approach. So C-Sparkle basically is pipelining existing systems to do various tasks. So in this case, C-Sparkle is pipelining a data stream management system to do the stream to relation operator, so to do the windowing and take care of the execution semantics. And the results are then pipelined to a Sparkle engine, in this case, the Gina Sparkle engine, to do the evaluation of the relation-to-relation operator. It's also important to note that the Sparkle engine is operating under the reporting policies on window close and non-empty contents, and it's using the RStream as a relation-to-stream operator. Another famous RSP engine is the sequels engine, and the sequels engine is taking what we call a white box or a native approach, because it has access to all the underlying operators. And this allows us to do various kind of optimizations. For example, it can do reordering of the query execution plan to improve throughput. Now, interestingly, compared to the C-Sparkle engine, the SQL engine is operating under content change reporting policy and has the iStream as the R2S operator. So since both of these engines, they have different execution semantics and continuous semantics, so they are producing very different results, making it very hard to compare their results, because they're using underneath the hood, they are producing different kind of result sets. This is also one of the goals of one of the triggers that led to the development of RSP4J, because there was a need for the community to have a theoretical framework to understand how these engines behaved and what their differences were exactly. So even though the community has done a lot of work in terms of benchmarking and comparative research, since many of these engines are using different internals, it's very hard to come up with a single winner or to have a decent comparison. So doing research in RSP can lead to a number of uncomfortable truths. For example, if you want to introduce a window operator, or you want to experiment with some kind of new optimization techniques, in many cases, you need to implement your own RSP engine from scratch, because the existing RSP engines, they're not built with extensibility into account or allowing to reuse certain aspects of their engine, because many of them are basically built to be as fast as possible. And the other thing that we already talked about, comparing different engines, is very hard because they all have different internals. And this is what led to development of RSP4J. RSP4J is a flexible API for the development of RSP engine and applications, specifically under RSP4J semantics. And RSP4J already offers all the necessary abstractions required for fast prototyping of RSP engines under RSP4J semantics. RSP4J can also be configured to reproduce the variety of RSP engines behaviors to promote specifically this comparative research, which is currently very hard. So RSP4J, it's an API allowing to reuse different abstractions that are already available in order to do some very fast prototyping and comparative research. So as we have seen, there are a number of challenges which specifically RSP4J is targeting. So the fast prototyping, because RSP4J is providing the necessary building blocks to quickly build an RSP engine. This benchmarking, because it can reproduce the behavior of different engine, and also dissemination, because it's specifically built on the theoretical aspects of RSP4J. So if we look at the architecture of RSP4J, what we see is many of the theoretical aspects that we already discussed are in here as well. For example, we see the different operators, the R2R, the S2R, and the R2S. We see the concept of the time varying graph. We see the tick and reporting policies, and so on and so forth. Next to that, we have all of these abstract components which can be reused, and also components which make your life easier if you want to build either applications using RSP or no RSP engines. For example, we have the IO package, which supports reading and writing to different kind of streams. For example, reading from Kafka, WebSockets from file, and so on and so forth. So basically, RSP4J tries to make your life as easy as possible when you want to do a new RSP engine or a new RSP application. So RSP allows to control RSP engine, like you would imagine, for example, the ingestion of the stream, registration of the queries, producing the results of the stream, and it can reproduce the execution semantics of common RSP engines. Currently, we have a number of bindings, meaning we have a number of engines that are using the RSP API. For example, Jasper with a Y is a native approach that is using RDF Commons and basically is implementing everything from scratch. We have the follow-up of CSparkle 2.0, which is also pipelining Asper as a data stream management system, and Gina for the evaluation of the R2R operator, but it's adhering to all the interfaces of RSP4J. Then we have work in progress on virtual knowledge graph called OntopStream. So RSP4J has all these abstractions, which you have seen. We have the data stream, we have the time varying concepts. And since RSP4J is very generic, it's also using a lot of Java generics, allowing you to, for example, create your own time varying relation or time varying graph. And also we have the encapsulation of the results type of the continuous computation. So just to give you an example, since RSP4J is using RDF Commons, a small example of how you can create a data stream. So for example, line 5, you can see the creation of an RDF stream. And then on line 7, you can simply create a new graph. And from line 9 until 12, you can populate this graph with a number of triples. Then on line 14, you can populate the stream. You can add a new graph to the stream and add a timestamp, in this case, 1000. And then all the consumers which are registered to the stream, it's not in this example here, but you can add consumers to the stream. They will be notified if something new has been published on the stream. So since RSP4J is adhering to all these abstractions or all these theoretical concepts, for example, you can also create your own time varying graphs. And as we have seen, the time varying concept is the graph relation or whatever you want to implement. It's a mapping from time to relations or to graphs. So there are basically two functions here, and Matteu's function that takes timestamp, and then another function to get the results out of it. So RSP4J is really like building on top of all these theoretical fundamentals of RSPQL. And of course, we have the results, result types. So because internally we're using Sparkle Algebra, which is using bindings internally. So it's important to say that RSP4J uses this concept of a continuous program, and continuous program evaluates a set of stateful functions, or what we call tasks, on an input data stream, and then populates the output stream, the result of the computation. It's important that you know that RSP4J has four generic types. The I type, which is the type of the input data stream, the O type, which is the type of the output stream, then we have W, which is basically the type of the content inside of the window, and the R stream, which is the type of the application of the R2R operator. So this might all seem a bit abstract. So how does it align with, for example, the RSPQL model or the SQL's model? So we have a stream of input type I, and then we can have a stream to relation operator going from I to W, producing, for example, time varying collections of time W. So the difference between traditional RSPQL and RSP4J internals is once you're in, let's say, for example, the relation to relation operator, you can go to different types as well. For example, the result of applying the relation to relation operator can go, for example, from graph to bindings. And then you can stream out the results, and we have results of result stream of type O. So in traditional RSPQL configuration, for example, if you want to mimic the behavior of the CSparkle engine, typically what we have is a stream of RDF graphs, and stream to relation operator, so the window operator, is consisting of graphs inside of the window. So this would produce a time varying collection of graphs, because inside the window there are graphs. On top of this, the relation to relation operator can evaluate triple pattern, basic graph pattern, everything that's Sparkle rating, and typically this is producing bindings. And once we have a time varying collection of bindings, we can stream the results out, but it depends, of course, on the query form. So for example, if we have a construct, the result type of the output stream would be graphs. If you have a select, it would be bindings. Now, why am I tell you this? Because RSP4J is very generic. Okay, I forgot this slide. So just to give you an idea, I introduced this already before. So the contents of the window are graphs. We apply the triple pattern as an R2R operator and stream out results. So RSP4J is very generic. So before we saw the configurations for the C-Sparkle engine, but RSP4J can also adhere to the configuration of the SQL engine. And the difference here is inside of the window, the SQL engine is already containing bindings directly. And this is behavior which you can mimic with RSP4J as well, because the stream to relation operator is going from graphs to bindings. So visually, it's a little bit different. So before windowing the data of the stream, basically you're already evaluating the triple patterns. So before you add something to the window, you evaluate triple patterns, and the window is consisting of bindings directly. And then the R2R operator is doing the joins. And because even though you have bindings, you still need to do some kind of joins. And then we can stream out the results. Of course, RSP4J also allows you to do some kind of querying. So a small example here, because later we do some exercises. So what we see here is from line 1 till 8, we're creating continuous query. And there we can already see the 4 types. So the first type is the input type. So we have a stream of graphs. Then we have another graph type, which is telling us that the content of the windows are graphs as well. And then we have 2 times bindings, indicating that the results of the application of the R2R operator are bindings, and we're streaming bindings out as well because we have a select query form. Then we see a query in RSP4J, as we have seen before. Just it's querying everything, and it's counting and the number of tuples in the stream. But what's important is that on line 10 till 13, we are creating a new task from this query. So basically what's happening under the hood is that RSP4J is extracting the different operators based on this query. So it's extracting the stream to relation, the relation to relation, and the relation to stream operators. And these are all present in this task. Later on, we will see how we can build them manually without defining it in RSP4J. And once we have this task, we can create this continuous program, which is also using the generic types. And the continuous program can be built by defining the inputs. So we have the in function, which allows us to define the input streams. We can ask different tasks, and we can add the output stream in there as well. And then we can add a number of consumers to see the results. Okay, we finally made it. We looked at a lot of backgrounds. We looked at the SQL model to get some insights of continuous semantics. We looked at the secret model to understand execution semantics. And we looked at RSP4J to see how we can understand the fundamentals of RDF stream processing. And we have seen that you can reuse these fundamental approaches using RSP4J. So I think now we can do a small break, and after the break, we can go into the more practical hands-on session exercises using RSP4J. So if you want to follow along, you can clone the GitHub repository and navigate to the correct folder. And then you can open the project with your favorite IDE, Eclipse or IntelliJ or whatever you're using. Maybe you're not using IDE, that's fine as well. If you're not into Java or you don't have Java installed in your machine, you can still follow along, for example, solving the queries on paper or thinking about which operators you can use. So I think now we can do a small break. I think that there has been reserved 15 minutes, so I will be back in 15 minutes. All right, so welcome back, everyone. And we will continue with the practical part of the second session. And like I told you before, the hands-on will be with RSP4J, which is a Java library. So if you have Java installed in your machine, please clone the GitHub repository and move to the correct folder. If you don't have Java on your machine, do not worry. I mean, you can still follow along. You can do some of the exercises on paper, for example, defining the RSP queries and thinking about which operators need to be defined manually. So since we've all been affected, and maybe some of you infected as well, through this whole COVID pandemic, we will do a short example and exercising using a contact tracing scenario. So in our COVID scenario, we have two rooms. It's a very simple setup. We have two rooms, a blue room and a red room. And in each of these rooms, we can do some kind of localization. So for example, each room, they have an RFID sensor. So we see the blue sensor and the red sensor in the blue and the red room. And certain people, they have RFID tags. For example, John has an RFID tag and has been localized inside the blue room. And Alice has also an RFID tag, has been localized in the red room. So if the persons have an RFID tag, they have this black dot with an R inside of it. We have other ways of doing localization, for example, through Facebook check-ins. And Bob has done a Facebook check-in. So he's manually posted that he was in the blue room, and Elena has manually posted that she is in the red room. And then we have another way of doing localization, which is more an implicit localization, and it's through the use of contact tracing. So in many countries, there have been some kind of app development that is detecting who has been in close proximity to any kind of other person. So when they get the news that they have been infected through COVID, we can trace back who has been in close contact to these persons. So we also have this contact tracing abilities. For example, David has been detected through this contact tracing app that he is close by to Elena, and Carl is close by to Bob. And the arrow that you see is like the close by relation or is with relation. And then we have a last source of information is the confirmed infections. So imagine that each person has to do a corona checkup or has some tests every few days. And then the hospital or the lab is streaming out the results, who has had a positive test results or who has been tested negative. So each of these sources of information, they are streams. So we have the localization stream, the explicit localization using RFID and the Facebook check-ins. We have the contact tracing stream, and then we have the confirmed infection stream. Of course, in a realistic scenario, all of this data would be published using different kind of schemas, different kind of formats. So we can imagine, for example, that RFID observations, they are published in JSON. We have the Facebook check-ins that are producing data in CSV, for example. We have XML and so on and so forth. So in a typical scenario, the data would be very heterogeneous because data is coming from very different sources. And therefore, the use of the RDF model is very appropriate because it allows us to integrate all this data together and to generate what we call a unified model. Now, to simplify a few things, I will just explain the data in table form and then also in RDF. So for example, for the sensors, the RFID sensor, basically we just know which sensor it was that has detected a person, in which room they are, and which person has been detected, because each person has their unique RFID tag. For the Facebook check-in post, we know which person did the post and where they checked in. For the contact tracing, basically we know who is with whom. And then for the hospital or the lab result test, we know which person had a positive or a negative post. So even though we posted them in table form, we will be using them in RDF. So for the RFID tags, we typically have an RFID observation stating who it was about, which room, and then maybe the most important triple, which person was in which room. And we see the same thing for the Facebook post. We also know who made the post, which room they were in, and then, for example, Bob is in the blue room. So for the practical examples, we will be using a generator, and the generator will take these two together in the same stream because they're both like an explicit localization. For example, Bob is in the blue room or Alice is in the red room. Then next to that, we have the contact tracing posts, which are more implicitly stating where a person is, because you just know with whom they are, but not explicitly in which room. So you still need to combine it, for example, with the RFID or the Facebook post to know where these persons are. So for the contact tracing post, we know, for example, that Carl has been detected and that Carl is with Bob. And then similarly for the test results, we know who it was about, and then the result of the test, for example, either positive or negative. So in this scenario, we'll be looking at 3 queries, at least definitely 2, and maybe the last one as an exercise to do at home. So the first query, you'll be looking at who is with whom and in which room are they. So for example, who is with whom, we can see that Dave and Elena are together in the red room. So to solve this query, we need to combine the RFID, the Facebook check-ins, and the contact tracing streams. The next query, we'll be looking at who is infected through close contacts, and also we'll be reporting in which room they were infected. And this requires the combination of all the 4 streams. And as a last exercise, we'll be looking at who is in a room where there has been an infected person, which is also looking at all the streams. So it's finally demo time. I will go to the first example using RSP4J, and then we'll do a number of exercises. So let me share a different screen. All right. So if you have clones, the data from the repository and went to the right folder, the RSP4J webconf folder in exercises /part2. What you will see is a structure. You will not have the solutions, but I have them with assignments and examples. And the examples are the demos which I will be showing, and then the assignments are what you can do to get some hand-on experience. So for each example and assignment, you will find some information. What the assignment is about, but I will explain everything, no worries. But the most important thing is that in this case, we'll be using a stream generator just to make sure that we have different people going from the red room to the blue room, and they're using different kinds of localization, either RFID or the Facebook post or the contact tracing. So we have different people using different ways of localization. So importantly, from the generator, we will be extracting 3 data streams, which are consisting of graphs. So the first one is the observation stream, which is both containing the RFID observations and the Facebook post. And basically, the most important triples are, for example, Alice is in the red room, or any kind of other person is in any kind of other room. And the same thing for the Facebook post, but they mostly generating the same kind of data. Then we also have the contact stream, or the tracing stream, which is saying who is with whom. For example, Carl is with Bob. And maybe also important to note that all of this data is internally published on a certain URI of the stream. So in this case, it's in the tracing RSP4J/COVID/tracing URI. And then lastly, we have the data that's been generated for the test results. For example, saying who has been infected and what the test result was. The generator can be configured, but I think it will be producing data every second. Now, the goal is, of course, to define a query that allows us to check who is with whom and in which room. So we will be doing this in RSP4J. 1 second. In RSP4J, so what we see is a very simple query. So we have the definition of some prefixes, then we have definition of the R2S stream. So how do we stream out the results? In this case, it's an R stream. Everything will be streamed out, which is in the result set. Then we are selecting the persons that have been detected and the room they were in. And here in the named window, basically, we are defining the stream to relation operators. So in this case, we have a window on top of the observations, being the Facebook post and the RFID observations. And we will have a window of 10 minutes with a slide of 1 minute. And the same thing for the contact tracing, also just for demonstrating purposes, the same kind of window. And then we can define our R2R operator on top of this window. So for the first window or for the observations, we will just check which person was in which room. And then we will be doing a join between these windows because we'll check if there was another person who was with this first person. This will create a continuous query where we have graphs as type of the input stream. We have graphs inside of the windows. The evaluation of the R2R operator also bindings, and we'll be streaming bindings out because we have a select query form. From this, we can create a task, and then we can generate a continuous program which takes as inputs our different streams. We can assign a task to it, and then we can assign the output stream. So if we will run this program, it should generate, for example, David was with Elena in the red room and Carl was with Bob in the blue room. And then, for example, we can see some duplicates because we are using a sliding window of 1 second. And then we see that, for example, Carl and Bob went from the blue room to the green room. Of course, you can make the stream longer because there's just a sleep statement here that's only streaming for 20 seconds. So this is how we can subscribe RSPQL queries using RSP4J. And I think now it's time for the first exercise. I will not go back to the slides, but if you go to the assignment folder, you can see the first exercise is query processing assignments. And in this assignment, basically we'll be checking who has been infected through close contacts and in which room has they been infected. So we will have to combine, let's say, the 3 streams. First one, the localization of the persons in different rooms, then the contact tracing results, similarly as we did before, so we can basically use that, and then also who had a positive test result in the last 24 hours. So you need to extend the query from the last exercise and also make sure that it's a join between the different streams and the test results. It's important to note that if you look at the contact tracing, for example, Bob was with Carl, that both Bob or Carl can be the ones that have been infected. So if you want to take care of that, maybe you can first try it without investigating this. But if you want to take care of this, you can use, for example, a filter operator that is checking these two options, let's say, using an OR statement. So if you want to follow along, basically what you need to do is fill in the query here, which is an extension of the query that we saw in the exercises. So if you look at the exercise, the examples, you can look at the query processing example and extend it from there. So I will leave you some time to do the exercise. And if you have questions, of course, please post them in the chat, or you can probably unmute yourself as well and ask the question. So I'll leave a couple of minutes for you to go through the exercise, and then I will go to the solution. So I think everyone had some time to fill in the query themselves or to try to fill it in. I mean, you can do it on paper if you don't have Java installed, but let's go through the solution. So I have the solutions and I will post the solutions later on myself. So in this case, we have to define 3 windows. So before we had 1 window for the observations, 1 window for the tracing, and now we also need a window for the test results, because the test results are valid for 24 hours. So we need to have a window of 24 hours to be able to join with everybody who we have been in contact with. So on our window of our observations, we need to know the localization of our person. For example, person 1 has been in a certain room, and then we need to join them through the contact tracing. So we have a person 2 who was with this person who has been either detected through RFID observations or Facebook posts. And then we need to do another join with another window where we need to fetch all the test results for a new person. And it's important that we filter out only the results that are positive. So here you can see that we introduce a new variable because it's important to note that, for example, either person 2, so if, for example, if Bob is with Carl, both Bob or Carl could be the one that had a positive test results. So therefore, introduce a new variable, and then we add a filter clause saying that either one of these persons, oh, there's a typo, either one of these persons can be the one that has been infected. So we can run this query and then we will see the results. So typically it takes some time before there is somebody with a positive result. So here we can see that Carl and Bob were in close contact in the blue room, and that it was Bob who had a positive result. We see a number of duplicates because we are using a sliding window, but we see in this case that David and Lena were also in close contact in the blue room, but it was Elena who had, in this case, a positive test result. So in this case, David should be the one that has to be alerted. All right. Let's get back to the slides. So of course, any other RSP engine allows you to define RSP queries, but the neat thing about RSP4J is that you can manually define all the different operators. So similarly as we have seen for CQL and for the RSPQL fundamental model, RSP4J allows you to define the stream to relation, the relation to relation, and the relation to stream operator manually. So RSP4J already includes a number of examples for the stream to relation, for example, the SQLs window operator, which consists of the bindings directly inside of the window, the CSparkle window operator, which consists of graphs, and also a number of implementations for R2R operators, for example, definition of basic graph patterns or triple patterns, and also all the implementation of the R2S operators, the R stream, the I stream, and the D stream. So how do you define, or how do you combine them, these different operators? So we can create a task. So before we saw that a task was generated from the RSPQL query, so we can manually define a task as well. For example, we can create a task on line 1 till 7, which allows us to add the S2R operator, the R2R operator, and the R2S operator manually, and optionally a number of aggregations as well. And this task can similarly be added, for example, to a continuous program. So you might imagine that you can add both a manually defined task and a query task to the same continuous program. And then you can add a number of consumers as well. Okay, let's first do another demo, and then we'll have another exercise. Okay, so the next example is the abstraction example. So, and in this example, what we will do is the query which we had in the first example, where we were just looking like who is with whom and in which room are they. We will define them manually, basically defining all the building blocks without using the RSP query syntax. So we'll be using the same stream generator, but similarly, now we can define all the engine properties. For example, we can define reporting policies, in this case on window close. We can define the tick, which is time driven, the reporting grain, and also, for example, the time instance. For example, in this case, the engine will start at timestamp 0. From these properties, these engine properties, we can create a new RSP engine, allowing us to create, in this case, for example, a C-Sparkle engine, which is a stream to relation operator going from graphs to graphs. So as input stream, you're having a stream of graphs, and the contents of the window will be graphs as well. And of course, we can define the name of the window and, for example, the width and the slide of the window. So in this case, we need to define two window operators, two S2R operators, and then we need to define the relation to relation operators, which needs to be evaluated on each window. So to make your life a little bit easier, we can define a number of prefixes, and then we can manually define, for example, a basic graph pattern consisting of a tuple pattern that is saying that person 1 should be in a certain room, in a variable room, and on a different window, we will have a person 2, which is with this person 1. So internally, a join between these two will need to happen. Of course, you can define these joining algorithms yourself as well, by extending, for example, how the task is being built. Now, the neat thing about this is that now we can define our task manually ourselves. So we can define the stream to relation operator. For example, on the observations, we'll have window 1. On the contact tracing, we'll have window 2. And then we can define which R2R operator needs to be evaluated on each window. And also we can define the relation to stream. In this case, we'll just be using R stream. And in this case, also, for example, the projections, like which variable should be reported. From this task, we can create a continuous program, which allows us to define the input streams, the tasks of multiple tasks that need to be evaluated on top of these streams, and then the output stream where the results should be published to. Optionally, you can also, for example, define the joining algorithm. In this case, we'll be using has join algorithm. So if we run this, we should see the same results as we had with manually defining the RSP queries. So in this case, we also have that Carl is with Bob in the red room, and that Deva is with Ina in the red room, and that then Bob and Carl going from the blue room to the red room. All right. So this is pretty neat because this allows us to manually define all the different operators. And it's also very easy even to do some kind of optimization because you have direct access to all the different operators. So as a small assignment, I will give you some time to define the different operators for the query. Who has been infected through close contact in which room, which we saw before, where we had to define like the 3 windows and join the 3 windows together, and also add the filter operator. So basically, I will give you a few minutes to do this exercise where you need to define the basic graph patterns and then add them to the task. So if you have any questions, please post them in the chat, or I think you can unmute yourself as well to ask some questions. All right, I will guide you through the solution. Also, I will be putting the solutions on GitHub later on if you want to look at them. So basically, for this query to see who has been in close contact and infected, because one of the other people had positive results, we need 3 windows. So one window for the contact tracing, one window for the specific localization either to RFID or Facebook posts, and also one window of 24 hours for the test results. So for the first window, we can define a basic graph pattern to know who was in which room through exact localization. For the second window, we need to check who was close by, let's say, to the contact tracing with another person, and then we added another basic graph pattern where we check that if we have a new person that had a positive result. We can also add these bindings, add these kind of filters where we define a filter where, for example, we check the value of the binding, because now we need to check the values inside the binding if this value is the same value for person 3 or person 1, or if person 3 was with person 2. So, for example, if you have Bob is with Carl, either Bob or Carl can be the ones that have been infected. Then again, we can build this task. We can build this task, so we define the windows, and then we define the basic graph pattern that needs to be defined on each of these windows. So we can, again, execute this, and we will see the same results as we had before. So by defining the different operators manually yourself, you have a lot of more ways to do improvements, to do research in the various components. And the neat thing is that RSP4J provides all the necessary building blocks to get you started. All right, there is another example and exercise, but I will leave it as something that you can do at home, where we'll be looking at some more reasoning applications to do some kind of inference in RSP4J. So I will close this part, and from now we can go to learning more about OntopStreams, and I will give the word to Matteo. So if you have any questions, please post them in the chat, or you can reach out to us later on as well.
Okay, thank you, Peter. I will share my screen. Okay, do you see it?
Yes, but only your...
Yes, it's empty. Now you should see the slides.
Yes.
Okay, perfect. So let me take a pointer. Okay, perfect. So welcome back to the second part of this tutorial, which is about OntopStream. So let's first of all, let's start talking about what is ontology-based data access. So ontology-based data access software are software which aims to solve very difficult data integration problems with the help of semantic technologies. So the idea of these softwares is to expose using a common layer using semantic technologies, which are queryable using, for example, Sparkle queries, several distributed database, which have several schemas. So the idea is that using this approach, we are able, which is also called the virtual knowledge graph approach, because we are creating a so-called virtual knowledge graph on top of this relational data. We are able to abstract independently of every database vendor, and to query using a common language all the sources of the data. even if they are different. And this approach is quite new, but is here in basically in the last 10 years. And the most the state-of-the-art solution right now is OnTop, which is the software I've let's say extended in a way that we are able to extend this virtual knowledge graph paradigm to the streaming virtual knowledge graph, where we are able to query not only traditional relational database, but also streaming data sources, like, for example, Kafka, Hadoop tables, streaming file systems, etc., etc. So the idea of this this software, which is called OntopStream, is to fill the gap between this problem, where on one side we have the data scientist and the analyst, which do not want to go to the specific vendor technologies. For example, do not want to query Kafka using the specific KSQL language, or do not want to query Hive using the Hive QL language, or query a file system using some other query language which abstract the file system. They want something which is able to expose it through a common layer. So the solution is OntopStream, which allow us to add a semantic layer in between our data, our raw data, and our analyst. And in particular, thanks to a set of mappings and an ontological layer, we are able to send an RSP4J query, so a continuous a Sparkle query extension with some nice addition like window conditions. So we are able to query using the window fashion over these traditional data sources, which can be ingested inside the Flink, which is a stream processing engine, which is able to ensure the nice, let's say, the nice replication properties typical of a distributed system. So on one side we have all the semantical enrichment we need, so that we are able to create an ontology which enriches our data also. And on the other side, we have the nice replication capabilities of a stream processing engine, plus all the data coming from several data sources, all integrated in a single place and queryable using a single query language, which is RSP4J. So the idea is that by sending this query, what we get is a set of SQL responses, which OntopStream is able to translate in a set of RDF stream of responses. So here we have a stream of RDF data, which is coming in an asynchronous way inside our data scientist notebook, for example. So OntopStream was developed, as I said, as an extension of the OnTop OBDA system, which is developed in Java. And as I said, it allows to query relational data streams. And the result is a set of RDF stream of responses. The software is available in two distributions: the OntopStream CLI, which allows us to query using a command line, and the OntopStream endpoint, which is the tool we will see today, which is the most advanced, which exposes an HTTP endpoint, which is eventually queryable using also a Python notebook. So today we'll see the Python notebook methodology because this is the most advanced. The command line usually is delegated to testing and developing of the data integration process. Of course, to design this software, we have to take the OnTop original software and modify it and perform a paradigm shift from traditional OBDA to the streaming OBDA. So we need to make some adaptation to this software. In particular, these are the main adaptation I need to implement. In particular, we needed to find a way to communicate to the stream processing engine. So we use the Flink JDBC driver, which is open source. We redesigned part of the OnTop engine. We designed the streaming virtual knowledge graph query rewriting approach, which we will see in the next slide. And finally, we have to include support for the results coming to in a streaming fashion to the end user. Of course, because we are moving from a traditional system which queries databases like MySQL or other SQL Server or other traditional databases to a streaming fashion. So taking into consideration all these data sources like Kafka or streaming tables, which are typical of a streaming distributed system. So talking about the streaming virtual knowledge graph approach, here we have a nice view of what is the streaming virtual knowledge graph approach and in particular, if you remember from the introduction about the ontology-based data access, the idea is very similar. So we have at the input an RSP4J continuous query, which and this query can express also in a window condition. This query is expressed over an ontological layer, so we have a vocabulary. Like for example, in the introduction, we have seen the color stream example where we have a vocabulary of colors. And the query over this ontological layer is then rewritten using a mapping engine, which is able to take the RSP4J query and rewrite it as a set of SQL queries. In particular, since we are dealing with Flink, this query will be rewritten in the Flink SQL query language. So the result is that we will have a set of Flink SQL queries over one or more data sources. For example, here we can have a Kafka streaming data source or maybe an Hadoop streaming data source here. So we have a wrapper which takes these Flink SQL queries, push the query back to the streaming data sources, get the data, translates back the results from SQL to RDF, and return the RDF response to the end user. Maybe in a windowed fashion if a window is explicited in the RSP4J starting query. Here is a more detailed view about the extension of the OntopStream, where we can see how we achieved this extension. So basically, what we have done in this work of extension is to take the original OnTop system, which is this part here, and we added an additional layer on top to be able to interpret RSP4J queries and window condition using the RSP4J library. And on the bottom, we have also introduced a streaming engine, which is able to get the data from the streaming sources in a streaming fashion and return in real time to the end user. Okay. Given that, now I want to introduce the tutorial part, which is the creation of a pipeline from the streaming data sources in Kafka, passing through Flink, Apache Flink, and OntopStream, and going into the end user notebook on Jupyter, where the end user is able to express an RSP4J query and get the RDF stream of responses based on some Kafka data which have been integrated. So here are the instruction to start our tutorial environment. So As before, use the you you have to clone the repository of this tutorial, so our repository, and then you have to start the environment. First of all, you have to go to the hands-on folder. So supposing you are in the main root of our tutorial repo, you have to write on the terminal cd exercises part 3, and then start the streaming the first part of the resources using the Docker Compose. So you will have to start Flink and Kafka and the Jupyter Lab. If you have Windows, you can use this command. If you have a Unix or Mac system, you can use this other command. Then, after the download and the starting of the platform, you have also to open a new terminal window and execute also this command, which helps to expose our Flink data to OntopStream for the next part. Okay, so execute one of these, either these commands and this command here after the starting of the platform. So I will show you how to make this process, also using my terminal. So supposing you are here on the exercises part 3 folder, you have to first of all start the Flink and Kafka by writing docker compose -f flink kafka win.yaml app if you have Windows, and this will create a virtual network and the resources. You will have the download of the resources so you will have to wait 5 to 10 minutes to start all this part, but you can just leave it running during the presentation. So after the download, it will start these resources. It will create the instances. You can see here a lot of output of the instances. And then once you have started the instances, you have to start the next the endpoint. So you have to open a new terminal and execute the second command. So the docker sec -it SQL client and the link to the mapping library. So these after the execution of this command, you should see a shorter message. So you should see reading configuration and the REST endpoint started. So from now on, we are able to establish a communication between OntopStream and Apache Flink for the next part of the tutorial. Okay, so given that, we can go back to our slides and see our business problem. So here is the business scenario I've proposed to you, where we have a typical data integration problem, where we have 2 car rental companies, which have the need to unify their information systems. Okay, so we have 2 branches, branch A and branch B, which have some differences in the way they manage the data in Kafka. For example, branch A uses 2 separate Kafka topics for trucks and cars, while branch B uses a different approach and stores all the rentals, so for cars and trucks, in a single topic, but keeps the user data in a separate topic. Okay, so we have some heterogeneity between these 2 data sources, which makes querying using, for example, for example, using KSQL, very difficult to query those 2 data sources, because we have to make a lot of join to integrate those data and think about. Here we are working with 2 branches, but if we have, for example, 10 or 20 or 50 branches, and we need to make a data integration using a handmade query with a query language, it's very difficult. So we need to find something which is more automated and which helps us to describe the data in a general way, and then the system will translate accepting a single, let's say, general query in RSP4J is able to translate the query over the specific branch data source. So we will have a specific query over the branch A and a specific query over the branch B, in which are different one with respect to the other. So here we have the goals of our business scenario, and in practice they are that they need to have a unified logical view so that their analysts are able to write a single query over several data sources which have several formats. And of course, since we are talking about a real-time system, we want to have a stream of results in real time or near real time. And a nice to have feature is also to have the data available with Python notebooks, so that a data scientist or analyst is able to take the data and manipulate using a simple Python script. Okay. And of course, the last requirement, which is the more general, is that the integration process should be scalable. So it's not important we have 1 or 10 branches. The process should be as easy as for a few branches or a lot of branches. Okay, so here is the high-level view of what I've seen before. So we have a vehicle, which can be a car or a truck, and a user which rents a vehicle, and the vehicle which is rented by the user. Of course, the problem at this level is that the branches uses different data structures. So just to see more in details the data structures, we can have a look at the topics of the branch A, where we have two Kafka topics, dealer 1 cars and trucks, where are stored all the vehicle information. So you can see here you have the ride ID, the rental ID, the manufacturer of the rented vehicle, the model, the plate, and the status, which can be start or end. Start when the rental is at the beginning, and when the vehicle is come back to the rental branch by the customer. And here we have also the user data in the same Kafka topic. Okay, so you can see we have some people which are renting some, for example, trucks, or some other people which are renting some other cars. And all this data are coming in a streaming fashion. So when a new rental is, you have to think about that. When a new rental is started, there is an operator on the RPC which adds the customer details and the rental details to the branch information system. Let's have a look also to the branch B. And as you can see, we have here a different scenario where we have a general vehicle topic, which takes data from both cars and trucks. So we have this type field, which says the kind of data. And we have also, again, the status of the rental and the data of our car or truck which we have rented. And we have also a user ID, which instead this user ID is used to make a join to another Kafka topic, which is dealer to users, which contains only the data about users. Okay, so a very different data structures. Okay, so given that we have our Kafka topics, the first thing we want to do is to organize the ingestion inside Flink to make the data available to OntopStream. So how can we make the ingestion in Flink? we need to use this table and SQL API, which is a set of connector for Apache Flink, which supports several data sources like Kafka, file systems, Hadoop, and other ones. And these connectors are available in a streaming fashion. So what we need to do is to specify let's say the ingestion process in a specific file, which is the sequenceclank.yaml file, which helps, which contains all the information to translate the data from, for example, a Kafka topic to our Flink dynamic table here. And of course, then we will need also another file to expose our Flink data to OntopStream, but this we will see later on. So in this, we have a file. What we need to express in this file is a table schema. So the dynamic table schema and the translation between Kafka and Flink, and the connector properties. So the address of our Kafka data source. So the problem is solved by something like this, where we express a table, which is a dynamic table, which is called in Flink, which is called, for example, D2 vehicles for the vehicles of the dealer number 2. We set that the type is a source connector, because we are taking data from Flink, from Apache Kafka to Flink, and that mode is append, because when a new data is available in the source, is also ingested in Apache Flink. So when a new data entered is added to Apache Kafka, this connector is able to get the data in near real time and put inside the Flink dynamic table in a streaming fashion. Then we need to specify all the fields, which is just a one-to-one translation of our Kafka topic fields. So we have the user ID, the write ID, the type, etc., etc. So these are just the fields of our Kafka topics we have defined before. And continuing to the description of this connector, we need to specify a very important field, which is the parser timestamp fields, which is a watermark field, which allows us to express query over a time window. So remember that our Kafka data has a timestamp attached to it. So here, what we are doing is to take the timestamp field in the Kafka topic and say that this TS field is a special watermark field, which is queryable using window-based queries. So over this very specific particular field, we will be able to express a Flink SQL windowed query. And finally, what we need to define is the connector to our data source. So we need to say that the data are coming from Kafka, the version of the connector, the address of our source, which is this one in our Docker environment, and the original schema of our data. So an entry in a Kafka entry that is ingested in Flink is composed of these fields here, which are the ones we have seen in the previous slides in the dealer 2 example. Okay, so now we have managed to ingest the data inside Flink. However, we have a problem, because our data are ingested in Flink, but these data are still not integrated, because we have just moved the problem from Kafka to Flink. Because if before we needed to integrate the data manually by using a KSQL query, now that we ingested the data inside Flink, yes, the job is a little bit more easier, but we have again to integrate the data by hand using a Flink SQL query, a very complex Flink SQL queries. And of course, this process is not scalable, because if we have 10 branches, writing an integration query involving 10 branches is very, very, very complex. So you will end to make some mistakes by writing the query. So we need to find an automated way to translate our a general query to a data integration query. And this tool to perform this data integration problem is OntopStream, which is able, of course, to create an unified logical view of the data. So the idea is that the user is providing a general RSPQL query, and then this query is translated over the several data sources. So we will have one query over the branch A, one query over the branch B, an automatic integration between branch A and branch B, and a unified response to the end user. To do that, we need, of course, to expose the data ingested in Flink to OntopStream. To expose the data, we will use the Flink JDBC gateway, which is a third-party service, which is open source. And this JDBC gateway is just a JDBC driver, which can be queried using Flink SQL continuous queries. So the idea is that now we have to develop an OntopStream configuration, which is able to create these Flink SQL queries over Flink. So let's go to the next part, which is the part about the data integration. So how we can integrate our two branches. So as I said, OntopStream automates the RSPQL to Flink SQL query rewriting, and so on the data integration, and also the relational to RDF response translation. So on one side, we have our RSPQL query. Remember this image we have seen before, which is written over a global ontology, which is describing the conceptual logical view of our data. Then this RSPQL query is written in a set of RSPQL queries. This RSPQL query is rewritten in a set of Flink SQL queries, which are pushed, in this case, registered over the streaming data sources, which are, in this case, the Flink dynamic tables. So the Flink tables for the branch A, and the streaming tables to the branch B. And then the responses will come back to this mapping engine of OntopStream, which translates back our relational responses in a set of RDF triples, which are returned to the end user. So in practice, by writing this RSPQL query, we don't need to know where the data are coming from. So if the data are coming from the stream processing engine number 1 or the stream processing engine number 2. We just need to write a query over the mapped data sources, and then we can get a unified response. Of course, to create this data integration stack, we need some tools to perform the translation. So first of all, we need the ontology to describe our data in a global view. We need to define a set of streaming virtual knowledge graph mappings. So the translation from RSPQL to Flink SQL, and so to the Kafka messages ingested in Flink. And finally, we need to establish the connection between OntopStream and Apache Flink. So let's start by designing our ontology. And in particular, in this case, what we will do is to design a very simple ontology where we have the concept of a vehicle, which comprises the subclasses car and truck. So using this little hierarchy, we are able to say that a vehicle is composed, car and truck are both vehicles. And another which will be useful for the data integration process of the branch B. And another interesting thing we can do is to express the rental end as a subclass of rental. So a rental which is ended is a specialization of a generic rental, which can be a start or an ended rental. Then after designing the classes, we need to design the relations, which are called also properties in the semantic web world. So we need to define some relation between our objects. So in particular, we define the user property, which is a relation from a vehicle to an user. So a vehicle as an user which has rented a given vehicle, and an user, there is also the vehicle property which connects the users to the vehicles. So user rented the vehicle. Okay. Finally, we need to define the data properties. So all the here are included all the Kafka message entries which are not included in the classes. So for example, here we use properties to express vehicle details, timestamps, and the user's personal information. So all these, all the string or integer or timestamp fields, which can be queryable and return us an information useful for our analysis. So just to make a recap, we have just to make a recap before going to the mapping part. We have a branch A, which has two Kafka topics, one about cars and trucks, and those topics are includes the data about the users who makes the rent. So let's see how we can create our virtual knowledge graph mappings. So as I said, OntopStream answers the RSP queries with a set of RDF streams of responses. But these RSP queries are based on ontological concept, but we need to define a strategy to translate our RSP queries to Flink. And here they comes in action the streaming virtual knowledge graph mappings, which are a set of bindings between a set of RDF statements and the Flink SQL selection queries. So here the idea is that we create a set of mappings which are composed by these three elements: a mapping ID, which is a friendly name, a source, which is the select field 1, field 2, field 3, etc. from the Flink dynamic table, and the target, which is the translation of this Flink SQL selection query in a set of RDF triples. So more practically, let's see how we translate our branch A and branch B data. So remember that we have these entities: rental, vehicle, and user, which are our entities. And we have these two topics, dealer 1 car, these two Flink dynamic tables, dealer 1 cars and dealer 1 trucks. So let's see how we can translate our data. So in practice, what we need to do is to create a two group of mappings. Let's call it group of mappings. One about started rentals and one about ended rentals, because we want to specify our source queries and filter where the status is start or end. And then once we have the information about the rental, if it's started or ended, we can write our RDF translation by saying that this thing here is a rental, which has a set of fields. So you can see you have a data property an information about the user. We have another little information about the timestamp. We have another information about the car plate, etc., etc. So the idea is that we are able to make, let's say, a translation from an RDF set of triples to a Flink SQL source query. And of course, we are able also to make this translation for the ended results. So when the status is end in our Flink table, we say that this thing here is a rental end, and we will also say add some information also here. And taking consideration that all these things here in graph parentheses are the fields which are selected from our Flink SQL query. So this RID field selected from my Flink SQL query will be put inside my RDF triple here at the moment of the translation. The same for this manufacturer result here will be put here inside this triple here, manufacturer, and will be replaced here. So the idea is that you create your selection query, then you write your RDF set of triples, and in this RDF set of triples, you will replace the data which are coming from the stream processing engine. The same, we can do the same also with branch B. Of course, the translation will be not exactly the same because we have a different data structure. So here we have a general table which keeps data about a general vehicle, which can be a car or a truck, and then on a separate table we will have data about our users. So here we can write our translation in a different way. In particular, what we need to do is in this case, we need to make a join to create a triple, because in this case, to write this triple involving both rental data and the user data, we need to make a selection over two Flink tables. So we will select some data from the D2 vehicles table, but also some data from the D2 users table. And then we will make a join based on the user ID. So basically, based on this user ID here and here, we will make the join between this topic and this other topic, which are ingested inside two separate Flink tables. And then once we have made the join, we are able to expose the data using this RDF statement. The same can be done for trucks, because we are filtering between types, which is car or truck, because we are saying that the plate, this entity here is a car, while this entity here is a car. While for the rental end, we don't need to specify if it's a car or a truck, because we have specified this information in the starting rental mapping. So once we have done with the mapping, the last thing we need to do is to create the JDBC connection. This is a very standard process, so you just need to put the address of your Flink JDBC endpoint, and then OntopStream will take care of contacting the endpoint and send a set of Flink SQL queries and get the SQL responses. So here is a very general passage which is made using JDBC calls. Okay, so this passage is common to all the cases usually. Okay, so said that, we can start OntopStream and let's see how the system behaves from an end user perspective. So what I'm asking to you is to open a third terminal and execute this command here, docker compose -f on top.yaml app. This command will start on OntopStream, which is already configured using the previous configuration I've explained to you, which is which is included in these 3 files. In particular, we have the OWL file, which is the ontology. We have the tutorial.obda, which is our streaming virtual knowledge graph mappings between RDF statements and Flink SQL queries, and the properties, which is the JDBC connection address. So let's start our endpoint. Okay, let's start our endpoint. So what you have to do is to take a new terminal and execute the command docker compose -f on top.yaml app. So also in this case, it will download on top from the Docker repositories, and then once is downloaded, you should see an ASCII text, an ASCII art text here, and the initialization of the OnTop platform. So you should see here that it's trying to contact our Flink instance, is reading some data from the schema of our Flink tables, and is able and now is ready to answer to our queries. So we can. So once we have started, we can go to the end user, let's say, user interface. So we can open Jupyter Lab by going to HTTP localhost 888. The password is test, and we can practice a little bit with the demo. So I invite you to go to this link that I will send you also on the chat. So you have to go to, let me open a new browser tab. So we need to go to localhost 888 and put the password test. Okay, and this will open our Jupyter Lab environment. So let me maybe take here the address and put in the chat. Okay, chat. Okay. And let me send them. Okay, so using this address, you should be able to access here. So here we have, you should see some files here. And in particular, let me zoom in a little bit. You should see 3 main files, which are Dealer1, Dealer2, and OntopStream tutorial. So the first 2 files, Dealer1 and Dealer2, are the data generator in Kafka, while the third one is the tutorial. So the execution of the queries over OntopStream, which integrates the data from the Kafka topics. So let's start to open the Dealer1 and the Dealer2 data generators, and let's run the code. So you need to execute the code in both the notebooks, Dealer1 and Dealer2, up to the cell, and keep running this the last cell, where you can see here the stream of data which is generated. So every 20 to 40 seconds, it will be generated a new piece of data in our Kafka topic. We can do the same with the dealer number 2 and start the data generator. Okay, so here we have a little debug again here. So you can see here that it is creating, you can see here a new entry which has been added to our Kafka topic. So now we are in the situation where we have the data in our Kafka topic, we have everything which is configured. So we can integrate these two branches using OntopStream. So we can open the third notebook, which is OntopStream tutorial, and try to execute the queries we are seeing here. So you can see here that we have our first query, and let me explain what is doing this query. So starting from the query, you have an explanation also on the slide, but I will follow the notebook so that we have, let's say, we'll go a little bit faster. So we have our first query, which is just an introduction of how to send a basic query to OntopStream, and how to use this Sparkle Stream wrapper, which is an extension of the Sparkle wrapper library, which I wrote to make possible the interaction to OntopStream using a Jupyter notebook. So this library is able to send an RSP4J query over OntopStream and get the result in several formats, for example, in TSV or in CSV. So we can specify, you can see we declare our endpoint using by creating a Sparkle Stream wrapper object. We set our query, which in this case is our goal is just to get all the car rentals. So it's just a very simple selection of some details about the rental stream. So we say that the variable car is of type car. So we only want cars, not trucks. We get the model, we say that the variable rent is of type rental. This variable rent is connected through the car relation to the car variable, and this rent has a start time and an user which is registered to the rental. So by executing this query here, in practice, what we are doing is to register a query in Flink, and later, after a while, because the registration it will take a couple of seconds, we should be able to see our. Let me check why is. Okay, the query is here. Okay, we should see the result in a while. But the idea is that, okay, here you can see the result. As you can see, it may take us a while because we need to make a double passage. We need to send a query to Flink, and then Flink needs to take the data from our Kafka topic. So there is a little bit of delay in the registration, but you can see that now we have our stream queries and new results are flowing. For example, here we have a rental made by Kevin Rodriguez of Audi TT. And if we go to one of the two dealers, we should see a rental of an Audi TT. Here you can see here that we have this the user with ID 3, which is Kevin Rodriguez, which has rented an Audi TT. But if we go back, okay, we don't have any new information. Let's check maybe another information just to see that the query is in real time. Just to let me check. Okay, we have a rental about a truck, so it's not what we are expecting, but I hope that it will come a rental about a car. Okay, we have a rental here. We have a new rental about a Mercedes Class C, so we should see here a rental in a while of a Class C, of a Class C. Let's check. It will take a little bit, but it should be updated. Okay, it is taking a little bit longer. Sorry. let me go to the next one, because we are a little bit. Of course, to end the query, you just need to click on the stop button, and the query will be registered after a while from Flink. But what I want to show you is, let's say, some more advanced feature of OntopStream. So, for example, we can also express. So remember that we are integrated data from two branches. So we are performing a data integration, and on top of this data integration, we can also express some, for example, filtering condition. So, for example, we can create a query to get both Porsche and Tesla car rentals. So here, by adding to the previous query a filter clause, which is in the RSP4J syntax and in the Sparkle syntax, a construct to filter, we are able to say that this man variable should be Tesla or Porsche. So by executing this query, what we should see is that we should get all the. Okay, let me make it this way. Okay. Let me see if that. Okay, we have some data which are flowing here. Okay, you can see here that some data are flowing. We have, for example, these people here, which has rented a Tesla. These other people which has rented a Porsche 911, and these other people which has rented a Porsche Cayenne. Okay, so you shall see here another data. So right now has come another data because we are continuously running this cell. So until we run this cell, we will get new data from our registered query. Okay, so if we stop this cell and we move to the next one, this query will be registered from Flink. Next, I want to show you another query, which is I think is very important, because here in this query I want to show you how to mix reasoning with data integration. So here not only we are using an RSP4J query to integrate the data, but we are also using reasoning. What I mean for reasoning, I mean this thing here, just to show you in the slides the explanation of the query. You have the slides on the repository. You can see that by saying that I want to get the rentals for Mercedes vehicles, both trucks and cars, and saying that select user plate model start, where our plate is a generic vehicle. What we are saying this, OntopStream is able to look at the ontology, which you have defined before, and say that, oh, look, that a vehicle is a superclass of car and truck. So let's extract as a result for our query both cars and trucks. But here we don't specify cars and trucks explicitly. We just say that we want a vehicle, and then by leveraging the ontological knowledge here in our ontology we have loaded into OntopStream, we are able to get both cars and trucks thanks to this hierarchy. The same is explicited also in this relation. When we say relation vehicle to plate, if we look at the ontology, you should see that the vehicle is a super relation of the relation car and the relation truck. Okay, so there are several implicit knowledge which we can take from the ontology to enrich our query. So let's try, and of course, in the last part we have a little piece of code where we are able to also to put the result in a file. So let's execute here the query and let's see what happens. Of course, here we will have a little bit of registration time. Again, as before, it will take a little bit. Maybe I should have started before. Let me check. Okay, the query is arrived. Okay, you can see here the data which are flowing. Okay, so here here are the rentals made up until now. When a new user will make a new rental, we will see if we left running this query, we should see a new row here. And at the same time, using this code here, we are also able to persist the data in a CSV file. So for example, if we go to the output folder and we open query3.csv, you can see that we have the exactly same results here persisted also in a query. So we have managed to integrate our data and also to persist back in a file. And also leveraging, very importantly, reasoning techniques. So thanks to this, now we need to be a little bit lucky. Okay, here you can see a new people has started a rental right now. Okay, so we can stop also this one that we have seen that is streaming. The last query I want to show you is very quickly, because we are a little bit out of time, is window condition. Because of course I say to you that OntopStream is based on the RSP4J, and the RSP4J includes a parser for RSPQL queries. So we can express also window condition. So in practice, we can also, with OntopStream, we can also express a query using a window, for example, to get all the rentals in using a 1 minute window. And this RSPQL query will be translated in the right Flink SQL window with query syntax. So since Flink SQL accepts streaming queries with window condition, we are able to translate this query here, that is better to run because we are out of time, from RSPQL window with queries to a Flink SQL window with queries. So here, of course, there is a little bit of registration right now, but we should see something in the very quickly. So the idea is that you can express window conditions. You can see here. Of course, here we are getting all the data up until now. If we left running this query for another minute, we should get the data, the new data get from the next minute. Okay, I think that's enough for the tutorial. If there are no questions, we can just you can terminate the platform by pressing Ctrl+C on the terminals. And if there are no questions, I will leave the speaking to Emanuele for a quick conclusion.
Okay, so let me share the screen. Okay. Here we go with the conclusions. Okay. So, thank you very much for following the tutorial and staying with us this long. Sorry for being slightly late. I will not spend too much on the conclusions. The the point that I want to make is going back to the introduction and specifically to this trade-off that we discussed before. The fact that there is indeed something like a Chinese wall that prevents to address velocity and volume at a given site. So still today, as exabyte of data per second are no way to go, right? So that's definitely something important to understand. But variety, that is making together with veracity the problem even harder. So what we tried to show you is that even if this is an extremely hard problem where you have to be aware of a Chinese wall between velocity and variety and volume, and the fact that you have two pressures that are making this trade-off even harder, still there is hope. And what we were trying to show you is that there is another trade-off somehow to be aware of, which is the trade-off between expressivity and reactiveness. Somehow, the more you want to be reactive, the less you can be expressive, meaning that the task, the continuous task that scales the most is filtering. You can filter millions of data points per second, no problem at all. If you think the routing of the internet is a giant distributed filtering problem. But as soon as you start to add a bit, so you start adding joins, you start adding aggregation, then things get much more complex. And that's why expressivity somehow will draw the reactiveness back. Now, I think that if you start positioning qualitatively in this space points from the streaming data processing, you will see that indeed there are streaming cases that are somehow easy at least to position qualitatively. So if you scale vertically, the blue points, definitely you will have both better reactiveness and more expressiveness than if you scale horizontally using streaming big data engines technologies. And this is because whenever you want to distribute tasks, you have to face the problem that the harder is what you want to distribute, the slower you will go, right? So in a sense, there are complex event processors, even very expressive complex event processors that scale vertically, and there are very few complex event processors that scale horizontally. And in any case, they take much, much longer than those that scale vertically. So if you want expressivity, indeed, you sacrifice reactiveness. If you want reactiveness, indeed, you sacrifice expressiveness. And in any case, scaling vertically, you will be in a better trade-off than scaling horizontally. Now, our benchmark is the line that you see drawn here in the middle, where we want at least the expressivity of SQL. We are not going to process relational streams on the web. We are probably going to process more complex heterogeneous streams. The case of RDF streams might be emblematic, but I'm not simply saying that all the streams on the web must be RDF streams. There can be, of course, JSON streams, as many of the streams that you find in the wild over the web, but probably very, very relational type of streams in the web will be rare. So our boundary is the ability to scale in this trade-off either vertically or horizontally. And what we want is at least the SQL expressivity. And so let me zoom to the upper part of this diagram. And I want to share with you where I feel the research that we did so far in this setting is positioning the various contributions. So on the one hand, there is the very first generation that was built something like 10 years ago. The C-Sparkle engine is definitely something that was a prototype, providing some reasonable level of expressivity, so at least the SQL one, but was not very reactive. And when we were adding the reasoning to the C-Sparkle engine, what we discovered was that was coming at the point to mostly bring it down to the static system. There were attempts to do even more expressive system like Italis that somehow were also trying to perform slightly better, which is good. And then other systems were positioning themselves in the trade-off, right? For instance, Sparkwave, Dynamite, they provide limited reasoning capability, but what they try to do was to be a bit more reactive, adopting a better algorithm or scaling. In the second generation, probably one of the best systems that I'm aware of is called Laser, done at the Vrije University of Amsterdam. And it implements a very expressive language that is called Lars, that comes from the University of Vienna. And that is probably one of the most expressive systems that was ever built. And it was built as a distributed system, so also quite scalable. On the same side, we rebuilt the C-Sparkle engine at a certain point, thanks to effort done by Pieter and others. And that was definitely one more, let's say, step towards an attempt to scale. In the middle here, I will place the C-Sparkle with reasoning, as you can see, slightly better than the previous generations. C-Sprite, the work of Pieter that I was mentioning before, I think that belongs to the third generation. And indeed, it is an attempt to get at least to the same scalability of the existing vertically scalable comprehensive end processor and data stream management system. And so it is really up to the state of the art, still being able to provide more than the SQL expressivity, which I think is interesting. Other systems like those that I want to mention are StreamQR and OntopStream that was presented by Matteo in this tutorial. What OntopStream does, as you saw, is rewriting down continuous Sparkle query, RSP4J query, sorry, into continuous SQL queries. And in that sense, you realize why one can claim to be as good as the state of the art, right? Because you are basically building whatever you want to do on top of the existing technologies. Okay. I hope that this was meaningful to you. If you have any question, of course, you can also drop us emails or contact us through the channels that you saw. There is a repository on Git where you can write discussions and contact us also there. So as a final slide, I would like to sort of go back to the requirements that we saw in the beginning and assess what is the positioning of web stream processing with regards to those requirements. The goal is to make sure that you understand where you may want to put more research effort in the next years in case you are interested. Definitely the web stream processing technology now is good, and we have a lot of studies that shows that it is possible to process web streams in a reactive way. I think that it was also largely demonstrated, but still I will not call that the problem is solved. The fact that we are able to integrate heterogeneous data sets, providing fine-grained information access in presence of complex domains. To me, there is more to explore. Maybe sacrificing the expressivity of the models, maybe sacrificing the level of heterogeneity, who knows, right? But definitely there is a space here to do more research. And where I really think that is worth researching is in whatever addresses the incomplete and noisy data. And because in this tutorial, basically, we did not cover at all the noisy data part of web stream processing. There are works there, but for a selection of topics, we decided to skip it. And as you saw, the level of incompleteness that we can deal of is the one that you can feel through deductive reasoning. And so there is a lot of incompleteness that you cannot at all fix through deduction, but is still there to be addressed. And also the scalability, I think that what Matteo showed you is in the direction to scale, and of course to scale a lot, but there is more research to be done there as well, because I mean, the word of horizontally scalable data same processor is not so easy as the SQL word. So being able to rewrite SQL query against Flink doesn't mean that you are able to rewrite a SQL query against any engine at any scale. But I will leave this consideration for another moment. So thank you again for coming to this tutorial or to watch the recording later on. Matteo, Pieter, anything to add here?
Not from my side. Thank you for the nice conclusion, Emanuele.
Yes, thank you, Emanuele, for the conclusion.
Okay, good. Perfect. So we were a bit late, but I don't think that was too much a problem. And yes, if you're interested, contact us. Bye-bye.